Good morning, honors chemistry students. Today, I would like to go through a particularly daunting task, which is how to use quantum numbers to predict the address for an electron in an atom. Quantum mechanics is a mathematical idea which seeks to determine or predict the probabilistic location of an electron in an atom. And so with that being said, I'm going to make an effort, a little bit of housekeeping here, make an effort to display to you the thinking that goes behind quantum mechanics, or I should say quantum mechanical theory. So what I would like to do is to take a look at quantum numbers. There are 4 of them that are under consideration today. So we're going to examine the quantum numbers and how they're actually derived. So for that being said, the first quantum number upon which all the other quantum numbers are derived is known as the principal quantum number. So the principal quantum number is determined by the variable n, which takes all the values from 1 to infinity. That being said, on the periodic table, you may note that there are 7 energy levels. We'll start with the first, n equals 1. You may also note that there is a second quantum number, which is known as the angular momentum quantum number. When electrons spin, they have rotational motion, and thus that is a different branch of physics, but angular momentum describes the momentum of electron when it's in rotational motion, and we say that angular momentum is defined by the variable L, which takes all the values from 0 to n minus 1. So in this case, if the principal quantum number is 1, the only value that L can take depends upon this formula, 0 to n minus 1. 1 minus 1 is 0, so 0 can only be 0. And quantum mechanics predicts that the angular momentum quantum number has a value of 0 if the principal quantum number is 1. In quantum mechanics, the fact that there is a number there, it does not particularly have value, but what it designates is a region of space that we affectionately refer to as an s orbital. There is a third quantum number, excuse me, which is called the magnetic quantum number. And the magnetic quantum number is designated by m sub L, which takes all the values from minus L to plus L. So in this case, if L is 0, the only value of m sub L can take ranges from minus 0 to plus 0. There is no minus 0 or plus 0, there's only 0. So the fact that there's a number there designates that there is one orbital in an s sublevel on the first energy level. So another way to look at this is the principal quantum number determines the energy level of an electron. The angular momentum quantum number determines the types of sublevel available to an electron in an atom. And the magnetic quantum number identifies the number of orbitals in a sublevel. And the last quantum number is referred to as the spin quantum number, which designates the spin of an electron and is identified as being m sub s, or spin of the electron, which can either be plus 1/2 or minus 1/2. Plus 1/2 is a clockwise spin, minus 1/2 is seen as a counterclockwise spin. So an electron on the first energy level that's in an S sublevel that has one orbital can have either a positive or negative 1/2 spin. For for hydrogen, the spin is denoted as positive 1/2. For helium, it would be negative 1/2, because in hydrogen, we depict the arrow in orbital notation as going up, and in helium, we depict the valence electron as one going up and one going down. I'd like you to think about another variable, which is n squared. N squared represents the number of orbitals in an energy level. So this would be the number of orbitals in an energy level. So in this case, if you take the principal quantum number and square it, we predict there's only one orbital. On the other hand, there is 2n squared, which predicts the number of electrons on an energy level. So the maximum number of electrons that the first energy level can hold would be determined by 2n squared. 2 times 1 squared is in fact 2, so that's how we predict that the first energy level holds a maximum of 2 electrons. So for hydrogen and helium, a proposed set of quantum numbers might be 1, 0, 0, plus 1/2, or for helium, 1, 0, 0, plus or minus 1/2, minus 1/2 for the last valence electron. So therefore, if you think about it, on the first energy level, there's just one orbital that holds 2 electrons, so the total number of electrons on the energy level is 2. For the second energy level, where the row 2 elements from hydrogen from lithium to neon, they have a principal quantum number of 2, which means if n is 2, the values of L range from 0 to 2 minus 1. So 2 minus 1 is 1. So the values that L can take are 0 and 1. 0 denotes an S sublevel and 1 denotes a P. Each value of L, once we know the angular momentum quantum number is 0, if you want to predict the magnetic quantum number, if L is 0, M sub L ranges from minus L to plus L, which again is only minus 0 to plus 0. So therefore, for an angular momentum quantum number value of 0, M sub L can only be 0. However, if L is 1, the values of M sub L can range from minus 1 to plus 1, which is how we predict that the P sublevel has 3 orbitals, one that lies along the X axis, one that lies along the Z, Y, and one that lies along the Z. Each orbital, and there are 4 of them, can hold a maximum of 2 electrons, which have spins of plus or minus 1/2. This gets a little bit daunting to draw this for each orbital or to write this down, but nonetheless we'll do that. If n is 2, the number of orbitals in an energy level is found by n squared, which would be 4. This number should coincide with the number of orbitals. 1 in the S, 3 in the P is 4, each one of it which holds 2 electrons, so 4 times 2 is 8. That's how we determine that there are 8 electrons on the second energy level possible. So the total number of electrons that the second energy level can hold is 8. For the third energy level, if n is 3, the values of L range from 0 to 3 minus 1. 3 minus 1 is 2. So the values that L takes are 0, 1, and 2. 0 denotes an S, again 1 denotes a P, and now we've introduced a different type of sublevel known as a D. So on the third energy level, there are 3 types of sublevels, an S, a P, and a D. S is spherical, P is dumbbell shaped, and D, there are a variety of shapes of d orbitals that are defined by mathematical functions. Again, if L is 0, m sub L can only be 0. So you note that S sublevels only have 1 orbital. However, if L is 1, m sub L can be minus 1, range from minus 1, 0 to plus 1. So again, P sublevels have 3 orbitals, which can hold, by the way, a maximum of 6 electrons total. On the other hand, if L is 2, m sub L ranges from minus 2 to plus 2, which means now in a D sublevel, there are 5 potential regions of space predicted, known as 5d orbitals. Thus, s orbitals hold 2 electrons, p sublevel holds 6, and the d sublevel holds 10. Again, electrons can have opposite spins in an s orbital, and likewise they can have opposite spins in each of the p orbitals. And again, in the d's, I'm going to have to kind of, sorry about that, squeeze these in here. This gets a little bit difficult to illustrate, but that's how we commonly think of the D sublevel, which has 5 orbitals that can hold 2 electrons each with opposite spins. So if n is 3, n squared would be 9, meaning that there are 9 orbitals predicted for the third energy level. 5 Ds, 3 Ps, that's 8, plus 1 S is 9, each of which hold 2 electrons. So we predict that the third energy level can hold a maximum of 18 electrons. Moving to the fourth energy level, things get even more interesting. If n is 4, the value of L ranges from 0 to 4 minus 1, which is 0 to 3. So we have 0, 1, 2, and 3. Now we're introducing a new type of sublevel. Once again, the fourth energy level has an S sublevel, a P sublevel, a D sublevel, and now we add an F sublevel. That being said, the S sublevel, if the value of L is 0, m sub L can only be 0. If the value of L is 1, m sub L ranges from minus 1 to plus 1. If the value of L is 2, m sub L ranges from minus 1 to plus 2. If the value of L is 3, as in an F sublevel, which take on some pretty interesting shapes that are mathematically determined, ranges from minus 3 to plus 3. And you may note that there are 1, 2, 3, 4, 5, 6, 7 orbitals in an F sublevel. Writing out the spin quantum number gets a little bit crazy. We know, for example, that the S sublevel can hold 2 electrons which have opposite spins with spin quantum numbers of plus or minus 1/2. Same thing can be said of the P sublevel. Same thing can be said about the D sublevel. This is not exactly the way I would want to do it, but it's the best that I can do for this video. I could show you a chart, but I feel like your needs are better served by me actually writing it out. And then I'll kind of skip here just a little bit. So we have to write plus or minus 1/2 7 times. That gets a little crazy. I think you'd agree. I think it's crazy, but I didn't want to drop you off to the point where you wouldn't be able to follow through. That's 6, right? 1, 2, 3, 4, 5, 6. And a last plus or minus 1/2. Once again, if the value of n is 4, the value of n squared is 16. 2 times 16 is 32. So this is how quantum mechanics predicts that the first energy level holds 2 electrons, the second holds 8, the third holds 18, and the fourth energy level holds 32. This, of course, continues on, but we'll leave that story for another day. And that being said, that should help you get through rows 1, 2, 3, and 4 of the periodic table quite nicely.